Today's video is related to the transient stability study, along with that grid islanding and also the grid stability. When the generator is working alone and the grid is not there, what will be the situation, means the stability, grid stability, means this power system network stability, and also the load setting scheme. So in this video I will try to cover. So now let's draw from the scratch. It is a grid. Let's say this is 400 kV, 400 kV grid. Short circuit current is 40, expired issue is 14, and another 400 kV bus I'm drawing here. In between there is a transmission line. So parameter configuration is not required. I'm not really going to put all these things. Only user defined I will put some value here based on my experience. Let's say these are the typical values. So all this resistance value, reactance value, susceptance value I've entered, and this transmission line length, let's consider 50 kilometer. We are done. Now we'll model 11 kV bus here. In between there is a step down transformer. This transformer rating 25 MVA, and I am considering typical Z and X by R values here. And now this is 11 kV bus, and here we are going to connect one generator. What's the rating of the generator is 8 megawatt, and power factor is 80%. Impedance, okay, let's consider the typical one. Okay, and we need to let's say there is a breaker, because we need to study the islanding condition whenever the grid will not be there. So we have model a circuit breaker here, and lamp load. Let's consider as 8 MVA. Two numbers 8 MVA loads are there. That's fine. So this modeling part almost done. This is done. Let's check that load flow, whether it is converging or not. Yes, it is converging. So this much of real and reactive power is flowing. Bus voltage 99.99%, and here, okay, transformer losses. Here bus voltage is 96.12%, and this, you can see this generator is showing in red So what to do? 8 megawatt generator. Why it is showing in red? Because let's give this rating. Let's give this rating. Let's consider this is 10 megawatt. No issue. And that's 9 megawatt. 85%. Let's consider 95%. Okay. So if we now run the load flow, this red part is not there. So it is delivering this 10 megawatt generator is supplying 9 megawatt load, because the total load is connected 8 plus 8 16 MVA. 16 MVA loads are connected here. So 9 megawatt supply is 9 megawatt is supplied by this generator, and the balance power is coming from the grid. So this is load flow, and let's move to the short circuit study. Let's create a fault here. 94 bus 94. This is 22.9 kiloampere. That means short circuit study is also converging. That is no issue. Okay, now let's directly jump to the transient stability mode. Transient stability mode, what we need to do before performing this transient stability study, we need to create event. Delete all these things. So event, what we need to do in case of any fault here in this transmission line, then the circuit breaker, the CV31, to be tripped, so that the entire grid connection will be isolated. So this CV31, I want to open this CV31 whenever there is a fault in this transmission line, and we will run this plant from this generator itself. So we are creating a fault here. So event name is fault at 1 second. 10 second is the total simulation time. We are now, what action we need to do, we need to open this circuit breaker, this CV31 open. That's all, nothing else. So in case of any fault in this transmission line at t equals to 1 second, at t equals to 1 second fault condition, that time the circuit breaker should open and the fault will be cleared. So also we need to plot this. Now this is generator 9, I think. Yes, this is gen 9. We need to plot this buses, all the buses, branches, all the branches. Okay, now let's run the transient study. So synchronous generator inertia equals 0. So whenever we are going to perform the transient stability study, we need to give the parameters like inertia, exciter, and governor. These three are required. So this is not done, that's why it is showing error. So inertia, this exciter, I will consider, let's say C1, sample data. Governor, let's say ST1. So here also I will use the sample data. drove maybe 4 you can consider. Okay, that's all. Now now let's run the transient stability. Yes, so what we can see, this is degree 38.88 degree, 1500 rpm is the generator speed. At t equals to 1 second, this breaker is open now. That means the grid is not connected. Now the grid is isolated totally, and here this angle, rotor relative rotor angle, you can see this is 0. Previously it was 38.88 degrees, so it is now changed to 0. And what you can see, if we set this, so units, yeah, now 9.47 megawatt power is generated by this generator, but the total connected load is 8 MVA plus 8 MVA, means 16 MVA. 16 MVA load is connected, but the generation is less. So what will happen in this case? Let's check. Obviously this bus voltage drops to 83.45 percentage, and let's check the plot here. What is the status? Synchronous generator gen 9. Let's check the speed, generator speed here. So 1500 rpm, it was the generator rated rpm, and at t equals to 1 second, the generator speed starts falling, and it is falling, and ultimately generator will be tripped. And also for this bus, this is bus 94. If we check bus 94, maybe frequency. Now the frequency, it was 100%. Previously it was 100%, but at t equals to 1 second, fault happened. That means the grid breaker is opened, and the generator is supplying to the loads the complete 8 plus 8 MVA 16 MVA loads, whereas the generation is less than 16 MVA. So that's why the frequency is falling down. So what we need to do, we need to we need to curtail some of the loads, we need to shed some of the loads. So how to do that? Now we'll see how to curtail the loads, right? Sorry. Yes, so now what I will do, go to event. Here I want to add another event, that means load shedding or islanding. Let's say fault happened at 1 second. Fault happened at 1 second. So I'm going to island the load at 1.1 second. That means after 100 millisecond of creating the fault, after 100 millisecond of creating the fault, I'm going to island this. So here the lump load lump 29 and 30, lump load 29. Let's say we are going to curtail by 50 percentage, maybe by 50 percentage of load, and the second load also. Let's say for this, sorry, this event. Islanding 1.1. We are going to curtail some of the loads. So lump load 29. We are curtailing 50%. This 50% load is shaded, and also another lump load, that is 30, that is also maybe by 50%. Okay, so we are done. Now let's see what will happen. Let's go to the generator speed. Yeah, so as you can see, this speed at t equals to 1 second fault, due to the fault the speed is reduced, and after that at t equals to 1.1 second, at t equals to 1.1 second, fault is that some of the loads are shaded. That's why the frequency is going off, speed is increased. This is the speed is increased. So basically speed is increased means frequency is also increased. So if we can check the frequency also. So this is the speed. If we want to check the frequency, we can do that. Bus 94 can check the frequency here. Yes, so this is 99.4 percentage frequency drop, 99.5 percentage frequency drop. So at 1.1 second, some of the loads means 50% of the loads are shaded. That means 8 plus 8 megawatt instead of 16 MVA. Now the loads, connected loads, are 8 MVA only, and this frequency is 102.1 percentage. So almost 4 percentage increased. But here one thing, if you notice, this frequency is not exactly 100%. It is not settled at 100%. It is more than 100%. Previously it was 100%, but after creating the fault and also after setting the loads, but the frequency is not coming down to 100%. So what may be the reason? What may be the reason? The reason is the generator is running in droop mode. So whenever grid is not there, we need to change this into isochronous mode. So what to do? Now I will create another event. At the same time at 1.1 second. Let's add this, means changeover at the same time means 1.1 second. Generator 9, change from droop to isochronous. So what I am doing, I am changing over at 1.1 second. The generator should run from droop to isochronous mode when the grid is not available there. Now let's run this and check the frequency once again for this bus, generator bus 94. Now let's check how much is coming. Yes, it is now settled to 100%. As you can see, previously it was 100%. It is now settled at 100%. So that's what we need to program. We need to set the program here in this governor. So from droop to isochronous mode, it should be changed because grid is not available that time. After creating the fault, when the circuit breaker is opened, so that time this grid is not available. So at that time the generator should run in isochronous mode, right? Now let's change something. Let's say islanding mode and changeover, those are at 1.1 second. But for the fault clearing time, means breaker opening, all these things, it may take some time. So we are changing, we are considering another 200 millisecond, that means total 1.2 second. Let's check what will be the impact if the islanding mode, means if the load setting is done after 200 millisecond, what will be the impact? And the same amount of load I am setting, means 50% load, I am keeping it same as it is. Now only we have changed that time, instead of 1.1 second, now it is 1.2 second. Now let's check the bus frequency here, 94. So what will happen? 101.1, and it is 100%. Yes. Now we'll change maybe this load to be shaded maybe 30%. This is also, we can consider 30%. So using this ETAP software, we can work out in this way how much load needs to be shaded to maintain the grid stability, this system network stability, or so that this generator should not be tripped due to the 81 operation, means under frequency over frequency relay. So that workout can be done. Again let's change, because we have changed, we have shaded the load, instead of 50%, now it's 30%. So 30% of 8 plus 8, 16 MVA. So 30% of 16 MVA means 4.8 MVA load is there only. Sorry, 4.8 4 4.8 MVA load is curtailed. That means 16 minus 4.8, that much of load is there. So now this is the frequency drop is 99%. This is 100.2%, right? Let's change this at 80%. If the lump load is curtailed 80%, let us check the bus frequency again. This is 103, 103 103 percentage of frequency, means over frequency. Why? Because we have set it 80% of the total loads, means 16 MVA. 80% of 16 MVA load is shaded. So due to the over frequency, the generator may get tripped, right? But the under frequency okay, 99% is, but due to the over frequency, that generator can be tripped, right? So we should not set that much of load, means 80% is. If we change again maybe 60%, so in this way we can work out how much load can be shaded. That's the that's the intent. 60% is, let's see. Yes, it is within limit. It is less than 1 or 2 percentage of frequency. So due to over frequency, the generator will not trip. Due to under frequency, the generator will not trip. So this is acceptable. This is acceptable. And obviously we need to check that critical clearing time also for this generator. Already there is a video. You can check out that video how to find out the critical clearing time to maintain the grid stability or to protect the generator. So this video is up to this. So what we have seen how the load shedding can be worked out, how much loads to be shaded, and how the events will be created. That means from the droop to isochronous mode, that changeover is also required to maintain the frequency. Okay, so in this video up to this.